All right, still talking about atomic theory. What's light got to do with it? So we'll talk a bit about light. So when we heat up a gas, they start to give off light. And an example in your everyday life would be a fluorescent bulb. Yes, long, skinny bulb filled with, I believe, mercury gas. You heat it up, and soft white light comes out of it. Scientists thought that every, each and every color could be emitted from these gases, but it's not actually true. So here's a gas, we heat it up, light comes out of it, we put it through a prism, which will spread the colors, and what you see here is that there's a band of red, a band of yellow, a couple greens, yes, and some blues here for this guy. We don't get any colors in here, right? No orange. Um, and this was a big surprise to them. Only specific colors. Here's another picture of what's going on. We've got a gas discharge tube, kind of looks like a fluorescent tube. It's attached to some source of current. Light comes out of it, goes through the slit, through another slit, through the prism, spreads it, and I get very specific colors being given off. And here they are right here. Yes. So only certain colors are going to be emitted. We call this picture of the different colors, we call it an atomic spectrum. Sometimes they use the word spectra, but only certain colors are going to be emitted here, and different elements will give off different colors. So here's a question I like to usually ask. So how do we know what gases are in the sun? Has anyone been there? No. What they do is they analyze light from the sun, just like up here, just like was done in this experiment here. They take the light coming from the sun, they spread it, they see exactly what wavelengths of light there are, and then they compare to known gases. Yes, and that's how we know that the sun has hydrogen in it and helium in it. It's when we analyze the light from the sun, we see the exact same bands in hydrogen and the exact same bands in helium. What is light? Is it a wave or is it a particle? Yes. And there is evidence to support and disprove both. And there's an argument for a long time in the scientific community. What is it? What is it? What is it? What is it? It's actually both. They call it wave particle duality. And one of the pivotal moments in this entire discussion was an experiment by Hertz. It was called the photoelectric effect. And according to classical mechanics, if you shine light on a metal plate, you can get electrons to get knocked off. And it was thought by the people who, classical physicists, that if you shined more light on, you would get electrons with more kinetic energy. They would come flying off more. So if I had 5 times as much light coming down, I would get these things flying off 5 times faster. But that's actually not what happens, which was a real surprise to them. What actually happens is that if I shine, here it says blue, but if I shine red light on them, I get electrons to come off, and they actually move fairly slowly. But if I shine higher energy, energy or light with a greater frequency, blue, onto this plate, they actually come off faster. And this was a big surprise to them. So it turns out in this experiment that the kinetic energy of the electrons only depends on the frequency of the light, not on intensity, which was just completely something that they weren't prepared for. And it was Einstein came along and he explained this in terms of light and it being actually small bundles of energy called photons. Small, let's call them packages of light energy. And Einstein came along and he explained this and he won his Nobel Prize for the explanation of this experiment. And so these are pivotal experiments and they really help us to shape the atomic theories to come.